Hi, I'm Ben-Yaakov. This presentation is entitled Practical Circuits Tutorial, Flyback, and I'm covering here the power stage. Now there is a disclaimer here that the controllers shown in this presentation are presented for educational purposes only. There is no recommendation implied for this particular controller, and other companies really offer similar controllers. Now the background of this presentation is a LinkedIn post that I've seen. Here is a attached schematics, which I've spotted a error in. There is an error in the schematics. And then I just looked at the schematics, which is a basic flyback converter, which is built around a controller by power integration. It's a nice controller. So I've decided that there is a point in actually covering the design of this flyback by itself, and then I'll also talk about the error that is in this schematic. Now, as it turns out, although a reference was not given, I was able to trace the origin of this circuit, and it is given in application notes by this company, Premier Magnetics, making magnetics, and they are actually offering this coupled inductor, and then they are suggesting this reference design around coupled inductor. So I'm going to discuss this circuit and talk about the inner working of it, the way it is built, and some key points related to the design, the power stage, voltages, powers, etc. So we are talking about a flyback which is built around a TOPSwitch. This is a line of controller by power integration. Power integration is the pioneer of this type of controllers, which incorporate both the power transistor and part of the control inside the unit. And in fact, this is a single die which has both the high voltage and the control. And it's not a simple matter, because this power transistor is first of all high power, and secondly high voltage. So we are talking about like 700 volt here, and then this control of course working at low voltage. So power integration introduces such a unit, and then other companies are today manufacturing something similar to that. So this circuit is really simple. It has a rectifier from the mains, and this can be a universal line between say 85 to 250 volt or something like that. So the ranges can be fairly high. It can be designed for a universal line. And then the coupled inductor is connected to the transistor. Then we have the output tap, which is controlled. This side is controlled. And then we have another one which is providing just bias to the transistor side of an optocoupler. So we have a signal coming from the secondary side, which is isolated. There's no connection between the ground. So this side is isolated. And then we have the signal, the error signal, coming through the optocoupler and then getting into the controller. And this is, as I've said, we are talking about the line of TOPSwitch controllers, and this particular one we are talking about is obsolete. It's not recommended for new design, but they do have a replacement also called TOPSwitch, but it's a different family now that is available. And the control of this unit works as follows. We have here the output voltage, and if the output voltage increases above the voltage of the Zener diode voltage and forward voltage of the diode here, then the current of the photodiode will increase, and then we'll have an increase in the current of the transistor, which is fed to the controller. Now the controller is built in such a way that as the current is increasing, the duty cycle is reduced. So by this we have a negative feedback, and then of course we might have some phase compensation depending on the system, but this is again a subject I'm not discussing in details here. And here is the inner works of this TOPSwitch. We have the power transistor, we have here a current limiter, and this is accomplished by this comparator, and then this is a reference for the maximum voltage across the transistor when it is on. So if the voltage of the transistor while on is above a certain level, this level, then it will turn off the gate. So the control is in fact measuring the voltage on the transistor, assuming a given RDS(on). Now RDS(on) is of course changing with temperature, but as a first order current protection, this is in fact very good. And then we have the modulator part, which has this triangular waveform, and the input is coming here. Now the input is a voltage, and the input is coming here. We have here a amplifier and a P-channel MOSFET, and this actually operates like a zener. This is a 5.7 volt reference. So when the voltage is above this value, current will start increasing very much because the voltage here will go down, and this is a P-channel transistor. So this is like a 5.7 volt zener, and then the current will be of course limited by this, they call it impedance, so it will be like VC minus 5.7 over the impedance. Now this is actually a resistance, but since it is current dependent, it's not very constant, it's in the order of 10-20 ohms, and it is not constant, so this is, I guess, why they call it DC. And then this current is actually developing a voltage here, which goes into the comparator of the PWM modulator, which has on the other side the triangular wave, in the conventional way. Now the power supply of this unit is actually coming from here. Okay, so this is the voltage of the power supply. You see it here. So this voltage is actually the voltage of the power supply. However, before operation, there's no output, so there couldn't be a power supply here. So therefore, power integration incorporated this arrangement in which from the drain here, which is connected to the DC bus, there is a current source, which at the beginning is actually charging this capacitor, providing a startup voltage for the unit. Once the unit starts to operate, then obviously there is a supply coming from this side for the capacitor to sustain the power supply voltage, and this will be disconnected. Okay, so there is a arrangement for a startup operation. Now the reference design that I've shown, which copied from the Premier Magnetics, is a bit different in a number of points, but there's one point here in which rather than having a Zener diode, they have this unit TL431. Okay, this is the optocoupler here, part of the optocoupler. This is the optocoupler, and this is then this unit here. So what is this unit? Now this is a adjustable Zener, you might say, actually first introduced by Texas Instruments, TL431, very popular. And what it is a circuit like this. The inner circuit here has a amplifier and a transistor, and then a reference which is 2.495. You might ask how come they have this strange number, and the answer is that this is a physical constant. It comes out of the fact that this reference is based on the gap, band gap of a junction, and so it has to do with the physical constant of the diode equation. So we have this reference, and so whenever the input here is higher or lower than this voltage, then it will interact with the amplifier and say if it is higher, then the transistor will start operating. So it is like a Zener diode. Up to the voltage of the reference, no current, and then as you go above it, even slightly, then immediately the transistor will start pulling current here, like a Zener. And this is very beneficial and very useful, because then by having this divider, you can actually adjust this voltage of the Zener. Because say if you have a 1-to-1 resistor, and this is 2.5, then this will be 5 volts, so this will be like a Zener of 5 volt. So why would you like to use this instead of a Zener? Well, there are a number of reasons, but one of them is that the Zener diode has a poor performance below 6 volt breakdown. That is, Zeners up to 6 volt are not that good because they have a very soft knee here, okay? So the stabilization is not very good. Only above 6 volt, the Zener, the regular Zener diode, start to have a very sharp knee here. So therefore, if you like to stabilize the circuit to have a reference below 6 volt, this unit is actually preferred. Okay, so they've used this unit, they have a 5 volt output, so it makes sense to use this unit. So the operation of this circuit is that we have this current coming here through the optocoupler, and then the transistor current of the optocoupler is then fed to the control terminal of the top switch. We have here another network. This capacitor is for the power supply. We need a power supply, but then there is another resistor, and this is in fact part of the phase compensation, because this network actually represents a lag lead compensator or a type 2 compensator, and so this helps to stabilize the system to provide phase compensation for the feedback loop. And again, I'm not going to dwell on it in this presentation. And then they have 2 capacitors between the ground. This is the output ground, can be connected anywhere. And then this is the line side, and so this could be hot, and therefore there is a difference of potential here. So you need a safety capacitor, and these are the so-called Y capacitor. This is not a Y connection. Y connection is at the input between the 2 lines and ground. So it's not a Y connection, but it is a Y-type capacitor, which is a safety capacitor. Now they've put here 2 capacitors, probably because of to sustain a higher voltage, okay? Because the voltage could be fairly high. These are 250 volt capacitors, so by having 2, you can go to a higher voltage as is needed. You will see it later on. Now the power of this unit can be estimated by looking at the outputs. Now we have a plus minus 15 volt 300 milliamp, and then we have a 5 volt 2.2 amp, and when we sum these up, we come up with 20 amp, which is okay for this particular top switch. Again, these outputs are not regulated, but this 5 volt is regulated by the feedback, as I've shown. An important question is whether this design operates the flyback in continuous current mode, CCM, or DCM. I'm testing it by looking at the ripple that you expect at the primary. Now it turns out that the inductance of the primary is 570 microhenry. This is from the datasheet of this unit. Now the worst case is when the voltage is low and then the ripple is the lowest. So I am now calculating what is the value of this delta I, okay? Now delta I is V delta T over A, and I'm assuming like duty cycle is 1, so this time is the period. Now this unit runs at 100 kilohertz, so it's 10 microseconds, 570 microhenry and 120 volt, so it's about 2 amp, the peak value. So if this will be running sort of continuously, the power coming out of the bus will be 120 times 1 amp, which is 120 watt, much more than we actually need for the 20 watt, of course. So the conclusion is that this unit operates at DCM, which has the advantage of having a simpler transfer function, and therefore the loop design for stability and dynamic response is simpler. So what about the voltage across the switching transistor? Now it has to do with the bus voltage and the reflected voltage to the primary during the off state. Now the turns ratio between the primary and secondary is 16 to 1. So if this is 5 volt plus say 1 volt on the diode, we have here 6 volt, and then the reflected voltage is about 100 volt. Now the DC, as stated here, can go up to 375. It's 475. However, in a flyback, since you have a leakage inductance, then when the transistor is turned off, you would expect an overshoot, and this is why they have here a Zener diode. Actually it's a TVS, a hefty diode. Here it is, so that it will clamp the voltage here. Now the voltage here has to be higher than, of course, the expected reflected voltage, and it is chosen to be here 200 volt. So we would expect a maximum voltage across the transistor of 375 plus the 200, 575, and in the steady state it will be 475. And as I've said, this particular unit has a maximum voltage of 700 volt, which is okay. Now, as I've stated, this family that is shown in the schematics is obsolete, and then they have a replacement, which is also a TOPSwitch, but of a different family. This family has another terminal here to which you connect a resistor to ground, and this will control the value of the maximum current. So the current protection now can be actually programmed by this resistor. But other than this family, Power Integration, as well as other companies, this is not just Power Integration, have introduced more and more sophisticated controller. For example, I'm showing the Power Integration family TOPSwitch, which is a unit which contains just about everything. It has also isolation within it, so you feed in the feedback into the unit on the output side. It has also control for a synchronous rectifier. So this unit is a more sophisticated one, and there are some others. And as I've said again, I'm not affiliated with Power Integration. I'm not recommending their product. They do have nice product, no question about that, but then other companies have also very nice controller. So now I'm coming to the issue of the common mode inductor or choke that is connected at the input to the unit. This is from the AC line. There is a fuse, and then there is this unit here. And what it is like two windings on a core, and the value of the inductance, this is from end to end, like if you measure from here to here, it will be 33 millihenry. But another parameter is very important, and that is the leakage inductance, because as I'll show, it is important in attenuating the so-called differential mode current. But unfortunately, the value of this leakage inductance is not given in the datasheet. Now, the way the windings are arranged, we have the dots here. This means that for the AC current, the main current going into the unit, like going this way and then returning this way, this is like a short. Has little effect of the current, okay, because the current coming in and coming out here. And this is because, like, if you connect 2 and 3 and look at the impedance between 1 and 4, you see actually a short here, neutralizing the other one. But if you have a current going this way, then you see this inductance. So let's see how this thing works. Now here we have a flyback converter, which is injecting current pulses into the input. This current pulses are passing through this capacitor at the output of this rectifier, and they are therefore generating a voltage ripple across the capacitor. Now this ripple now is an input to this path here. You see that it includes this leakage inductance and this capacitor, while the unit itself, the coupled part, is neutralized because we have a current going this way and then it's going this way. So what we have here, you might say, is a low pass filter, this inductor and this capacitor. So therefore it will attenuate very much the voltage here, depending on the values, of course, and so that the remnant voltage here, which is causing a ripple current into the input, will be reduced. So this is how the differential current, okay, is attenuated by this common mode filter. And then we have the common mode part, and this parasitic current is caused by capacitance between the unit itself, the switcher, the board, you might say, and ground, and I'm talking about earth, that is the actual ground around the system, through capacitance coupling. So there is a current injected here, and then it'll go all the way through ground and then back into the unit. Now in this case, the element that is actually attenuating or blocking this current to a certain extent, you might say, is this common mode, because now we are talking about the impedance between here and here, and this is how the common mode inductor helps to attenuate the common mode current. But as I've said, due to the leakage inductance, it is also helping to attenuate the differential current. So how is this tested? Now, if you go to a certified laboratory, or if you do yourself these tests, then you need a LISN, line impedance stabilization network, which has an inner circuit which looks something like that. Now, the purpose of these inductors are actually to block the current and to maintain it in this path here. So they are passing through these 250 ohm resistors, and this is the output of the unit. So here you connect the spectrum analyzer and you look, and on this 50 ohm refer to ground. So now if we have this differential mode current, so we have the current going this way, so you see that in this 50 ohm it goes this way, in this 50 ohm it goes the other way, so therefore the phases here will be opposite. Now for the common mode, we have the path going this way and then through the ground back into here, and then we have a current going this way and then this way, and then of course they have the same phase. You can distinguish between the differential and common mode by this information. So now I'm coming to the circuit diagram that was attached to the LinkedIn post. What they are showing here is clearly an error. It is connected incorrectly. This is supposed to be the filter, the common mode filter, and you see that rather than having it in the right connection like this, it is connected like the input is here. Okay, it's here. Well, first of all, it doesn't do what it's supposed to do. That's the first point. But more importantly, this connection is very dangerous if indeed you'll build a system that will be connected like that. And the reason is that we are connecting 250 volt to this winding, which is not designed to sustain 250 volt at 50 hertz. This is a high frequency component, it's not a low frequency component. So the core, the size of the core, the number of turns are not suitable to really this type of an input. So if you will connect the line to this winding, the core will saturate, and this means that you have a short. So you have a short on the input, and then either you'll see first smoke here, or the fuse will be faster and it will disconnect the system. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.